by our definition. So then you just use multiply this log function with phi n. You get this sum. It's just a reformulation of that product. And then you just take the exponential of this to get the product I just erased. So now forget about. So actually, this is the product form is not the thing we will use. We will use this formulation. Just from the equalities I've just erased, we know that the zeta function is a formal power series with this an is the number of effective divisor of degree n defined over the base field k. So if we want to compute the zeta function, we need to, it is equivalent to compute the number of effective divisors of given degree over the base field k. And to compute this number, we need to use a very important theorem in algebraic geometry, which is called the Riemann-Roch theorem. So before I state the Riemann-Roch theorem, I have to give you more notations. So that E be a divisor on the curve C defined over K. Then I define a set which is denoted by capital LD. So this LD is all the non-zero rational function on the curve C with the property that if you take the principal divisor associated to this rational function, you recall you just take all the zeros and take all the poles and add them together. Each of them, the coefficients are the multiplicity of the zeros or the poles. You get such a principal divisor, and you add this principal divisor with the divisor you fix at the beginning. You require that this is bigger or equal to 0, or in other words, this sum should be an effective divisor. Okay? And then we take the union with the zero function. The zero function, of course, is actually it's a regular function defined on the curve C, but there's no way to define the principal divisor associated to the zero function. So we need to first exclude the zero function, and then we add them back at the end of the definition. So this is just a set. We have some fact on this set. The first one, this is a finite dimensional vector space over K. So actually the only thing which is not that trivial to check for this fact is that if you have two rational functions, which belong to this set, then their sum is also a function which satisfies this inequality. So here you should use the fact that if you, for any point P, which is a closed a k-bar rational points of the smooth projected curve, we consider the order of the sum of these two rational functions at a given point P. It should be bigger or equal to the minimum of the order of these two functions. So you can check this inequality by yourself, and based on this inequality, you can show that if we have two functions from this set, you take the sum, their sum is still an element in this set. Okay? And of course, if you have an element here, you just add a non-zero scalar to this function. Of course, it does not change this principal divisor. Of course, so the same inequality still holds. Probably the more non-trivial thing is this vector space has finite dimension, but this is a result you can show in by algebraic geometry. But today I cannot give a proof of that. So you just assume this, the fact that this is a finite dimensional vector space. And its dimension over K is denoted by small LB. Okay? And I will list some other properties of this dimension, which you can check. Not very difficult. So if you have two divisors and they are linearly linear equivalent, then the dimension of this the associated vector space should be the same. And next thing is you just consider the zero divisor. Is D is 0, then in this vector space, this just tells you you need to consider, this inequality tells you you need to consider all the regular function on the curve C with no poles. Okay? So this is the meaning of this equality. But I told you that you can imagine the projected curve as the projected smooth curve as an analog of the Riemann surface. And the only homomorphic function defined on the whole Riemann surface is the constant function. Similarly, the only regular function defined on the whole projected curve is the constant function. So here you should have the constant function. In other words, it's one dimension. Finally, if you start from a divisor whose degree is negative, then the dimension of this vector space is 0, or in other words, this set consists of a single element, namely 0, the 0 function. Because if the sum of these two divisors is effective, in particular, its degree must be non-negative. But we know the degree of this principal divisor is 0. So if the degree of this divisor is 0, the sum of this divisor should have negative degree. It cannot be effective. Okay? So in other words, it is empty for this part, and you only have 0. So the dimension is 0. Now I can state the theorem, Riemann rule. Again, I always fix the smooth projected curve over the base field K. Then there exists an integer G, which is non-negative. This is called the genus of the curve. And a divisor is called Kc. This is called canonical divisor. Such that for any divisor D, we want to compute this dimension, but this theorem cannot tell you the dimension directly. It is related with the dimension associated for this divisor. It is equal, the difference is equal to the degree of the divisor minus G plus 1. Okay, so this is the statement of the Riemann-Roch theorem. It helps you to compute the dimension, this LD, but actually, if D is not very special, you cannot compute it directly. You must relate this dimension with this dimension. But this theorem is good enough because it has some important corollaries. The first one, in that theorem, you just take the divisor to be the special divisor. You just take to be the zero divisor. Then we know that this L0 is 1, and the degree of the zero divisor is 0. And then you compute that the dimension associated to the canonical divisor is G. Then you take the divisor to be the canonical divisor. Then the second part becomes L0, which is 1. From this, we see that we combine with the first part of the corollary, the degree of the canonical divisor is 2G minus 2. And finally, which is the most important thing, is if the degree of the divisor is large enough, actually we have a very explicit lower bound. If it is bigger or equal to 2G minus 1, we know that this dimension must be 0 because the degree because the degree of this difference of this divisor is negative. Because the degree of this divisor is 2D minus 2, and the degree of the divisor D is bigger than the degree of this divisor. So this is a divisor with negative degree, and you use the last part of this remark. This dimension must be 0. And then for such divisor, you apply the Riemann-Roch theorem. We see that this term vanishes, and the Riemann-Roch theorem will really give you a way to compute this dimension. Okay? So, if you have never seen this Riemann-Roch theorem before, it might be difficult for you to understand this theorem. So my personal suggestion is you start from some simple cases. For example, you just assume that the curve C is the projective line, and you try some simple divisors to really compute the left-hand side and right-hand side. And in this way, you can get some feeling about this. So now we want to use this Riemann-Roch theorem to compute this AN, this number of effective divisors of degree n defined over k. So this is the number we want to compute. So how is this number related with this dimension? So give the proof, I need to introduce some numbers. First, we know that I introduced two subgroups for the group of divisors. The first one is the subgroup consisting of the degree 0 divisors, and as a subgroup, it has another subgroup, namely the set of the set of principal divisors. Then I consider the quotients. It turns out that the quotients is a finite group, and its canonical number is denoted by h. This is only true for smooth projected curves defined over a finite field. The finite field condition is very important. In general, if K is an algebraic closed field or it's an infinite field, this is not true. This is only true for finite field. And also, I need to assume a fact. There exists a divisor C1 of degree 1 defined over K. This may not be true. This question is closely related to the question of the existence of a K rational point on the curve C. If you have a K rational point on curve C, you just take that point as a divisor, then you get a divisor of degree 1 defined over K, right? But the converse is not true. The existence of such a divisor does not imply the existence of a K rational point on the curve in general. And as I have told you in the previous lecture, if the genus of the curve C is large, there might be no K rational points on the curve C. But in the contrary, there always exists a divisor of degree 1 defined over any finite field. If you assume this fact, then we have a bijection for any integer n. We have a bijection between the set of divisors of degree n and the set of divisors of degree 0. Because if you start from a divisor of degree n, you minus n times C1, you get another divisor, and its degree is 0. So in this way, you get a bijection between these two sets. And here, what we want to calculate here, we want to calculate the number of effective divisors of degree n. So in other words, we want to compute how many effective divisors on the left-hand side. So here, if I choose a set of representatives of these quotients, I denote it by sigma 0, then I consider so this is a set of representatives of degree 0 divisors under the equivalence of linear equivalence. And as for each element in this set of representatives, I add n times C1 to the divisor, I get a set of representatives of this set under the linear equivalence. Okay? Then I can have a description on these sets. This is the number, the cardinality number of these sets is what we want to compute. We want to compute all the number of effective divisors defined over K with degree n. But we can write it as a disjoint union. We want to use the linear equivalence to divide these sets. Any such divisor must be linearly equivalent to some representative in this set. So I just divide the whole set into the disjoint union according to the representatives under the linear equivalence. But what does this set mean? This set means that here you just get all the effective divisors, which is linearly equivalent to a given divisor. So that means you can any such divisor should be of this form. First, it should be linearly equivalent to the given divisor C, so it should be of the form C plus a principal divisor, and moreover, it should be effective. Okay? So now let's consider the case. Here, I consider all the divisors, but on the other hand, I can consider all the possible rational functions which may appear in this sense. So, what are these functions? What kind of condition these functions should satisfy? It should satisfy C plus div, this is positive, and f is non-zero, and together with the f equal to 0, the zero function. So this is the set LC we have just defined. And from this set, first we remove the zero function, and then we apply a div here. Then we get a divisor in this set. But we know that this set is a finite dimensional vector space over K of dimension LC. Okay? So in total, we have Q to the LC elements in this function. But when we want to apply this div operation, we need to remove 0. So here we should have Q to the LC. First, you need to remove the 0 function, but it is possible that two different functions will give you the same div. Namely, if they are different by a scalar, then they give you the same principal divisor. So you need to divide it by Q minus 1. That's the number of elements in this set. So that's also the cardinality number in this set. And then we take the sum, we get the number of effective divisors of degree n. We have this an is equal to, you take the sum for all C, C is inside this representative, Q to the LC minus 1, Q minus 1. If you want to simplify, 1 over Q minus 1 is a constant. And then you take this sum. Then first, you take the sum for all these powers of Q. And then, the second part, you take the sum for all these ones. But they are exactly H elements in this sigma n, because sigma n has the same elements, same number of elements as sigma 0. So this here we have. So this way we give a computation of the number of effective divisors of degree n over k. And we can use the Riemann-Roch theorem to compute these numbers. So that in the next lecture, I will continue with the computation. And I think we are very close to the proof of the rationality. Sorry.